Welcome back to Math 104. Having worked out the first 5 rows of Pascal's triangle, the task is now to work out row 6 and row 7. Remember that we start counting with row 0 here, so row 0, 1, 2, 3, 4, 5. Other than the ones at the beginning and end of the row, each entry is the sum of the 2 entries above it. So this one is 6, 5 plus 10 is 15, 10 plus 10 equals 20, 10 plus 5 equals 15, 5 plus 1 equals 6. Similarly, in row 7, 1 plus 6 equals 7, 6 plus 15 is 21, 15 plus 20 equals 35, and now notice we're going to see exactly the same numbers as we come back down the other side. 20 plus 15 equals 35. 15 plus 6 equals 21, we've seen that before. 6 plus 1 equals 7, we've seen that before. So notice how every row here is symmetrical about the center. 35, 35, 21, 21, 7, 7, 1, 1. If we needed to, we could continue row by row as far as we wished to go. Now let's look specifically at row 7 of Pascal's triangle. Row 7 is the row that knows all about 7-letter words, consisting of L's and R's. All such words are accounted for in row 7 of Pascal's triangle. There is one word with 0 R's and all the rest L's. There are 7 words with 1 R and all the rest L's. There are 21 words with 2 R's and all the rest L's. Each location along row 7 knows about 7-letter words with a certain number of R's and all the rest L's. It's useful to have notation for this, for singling out each address within Pascal's triangle. This notation, C parenthesis 7, 0, refers to the value that lives in row 7, entry 0. And that's this entry right here. This 1 is designated by C parenthesis 7, 0. That means the number of 7-letter words with 0 R's and all the rest L's. And when you see that symbol, you should read it as 7 choose 0. We'll come back to what this has to do with choosing. There's another notation that's often used, where the 7 and the 0 are written vertically enclosed by large parentheses like this. This also means go to row 7, entry 0, and see what number is there. Similarly, 7 choose 1, whether it's written this way or in this vertical way, 7 choose 1 means go to row 7, look at entry 1. So this 7 right here equals 7 choose 1. That's just what we mean by the notation 7 choose 1. It's telling us to go look up a certain address within Pascal's triangle. Had it said 6 choose 1, it would have been telling us to look at row 6, entry 1. So 7 choose 1 refers to this number in Pascal's triangle, which has a specific meaning. It means the number of words with 1 R and all the rest L's. There are 7 different words with 1 R and 6 L's. Now, why is this called 7 choose 1? Suppose that you had to take a trip and the directions you were given were that you had to travel 6 steps to the left and 1 step to the right in whatever order you wish. What matters is that there be 6 lefts and 1 right. It's up to you to choose the order. How many choices do you have? You have exactly 7 choices. That's another way of saying that there are 7 words with 6 L's and 1 R. How about 7 choose 2? 7 choose 2 just means go to row 7, entry 2, and see what number is there. That number is 21. There are 21 words with 2 R's and all the rest L's. That is 7-letter words with 2 R's and all the rest L's. So that means 5 L's. If your directions were, take 5 steps to the left and 2 steps to the right, but the order of the 5 lefts and the 2 rights is up to you, how many choices do you have? You have 21 choices. That's why we call it 7 choose 2. Similarly, 7 choose 3 equals 35, and so on down the line until you finally get to 7 choose 7. And that's 1 as it would be at the end of any row. Now, how does this help us? If the outcomes of an experiment are equally likely and can be represented as words in a 2-letter alphabet, then we can read off probabilities from the appropriate entries of Pascal's triangle. This is a crucial point. Anytime you see this kind of experiment, which has become our favorite kind of experiment in this course, that is, an experiment where the outcomes can be represented in this way as words of a certain length in a two-letter alphabet, your immediate response should be to go to the corresponding row of Pascal's triangle, because that row of Pascal's triangle knows about such experiments. For example, a family with 7 children is selected at random, and the birth order of boys and girls is observed. Assume that for each birth, having a boy and having a girl are equally likely. Great! We just read all the magic words that tell us this is a job for row 7 of Pascal's triangle. This is an experiment where the outcomes can be represented as 7-letter words in a 2-letter alphabet for boys and girls. Great! It's a job for row 7 of Pascal's triangle. Our response is write down row 7. Even if you don't write down anything else, the fact that you write down row 7 right here will earn you some partial credit. Let's first ask, how many different possible outcomes are there for this experiment? Now, we already have a way of answering this question, but now we have a new way of answering it. The old way of answering it was that this is a 7-stage process with 2 possibilities at each stage. Therefore, there are 2 to the 7 different possible outcomes. That equals 128. That is a perfectly legitimate way of answering this question by using the multiplication principle. Now, someone watching this video is thinking, hey, wait a minute, I thought we got into this whole Pascal's triangle business because there was some problem with using the multiplication principle. Wasn't that right? Good memory. You are right that there was some problem using the multiplication principle directly to find this 35, or that 21, or that 7. And it's true that we did need to develop Pascal's triangle and the various thought processes behind it in order to come up with these numbers. But as for the experiment as a whole, the sum total of all different possible outcomes in the experiment, that was indeed a job for the multiplication principle, and we were using the multiplication principle already before we got into this whole Pascal business. So the total number of different possible outcomes is indeed 128. But notice, if you add up all the entries in row 7, they do indeed add up to 128. And they had very well better, because of what these various numbers mean. What's the total number of 7-letter words? It's all the words with 0 R's, together with all the words with 1 R, together with all the words with 2 R's, together with all the words with 3 R's, etc., all the way up to all the words with 7 R's. This sum is counting the same 128 total number of different words, but it's broken them down by type. Once we have row 7 of Pascal's triangle written out in front of us, it becomes very easy to read off the probabilities of each of the following events. The family has 0 girls. That's just 1 out of 128. 128 because we just figured out that's how many different outcomes there are in such an experiment, and 1 because of this one right here. How about the family has 1 girl? Of all the 7-letter words with B's and G's, there are 7 such words with 1 G and all the rest B's. That's counting exactly the number of outcomes in this event. So 7 out of 128 is the probability of this event E1. Similarly, that the family has 2 girls, that's 21 out of 128, namely this 21 right here. That the family has 3 girls, that's 35 out of 128, etc. For exactly the same reason why row 7 of Pascal's triangle knows how to count how many words there are of a certain type, it also knows how many outcomes there are in each of these events. This means that we now have a straightforward way, using Pascal's triangle, to find the probability of any event of this type, no matter how many children are in the family, and no matter how many girls or boys we are inquiring about. Now, a key point for working with these kinds of events is that they are mutually exclusive. For example, the probability of 5 girls or 6 girls, so in our notation that's the probability of E5 union E6, we could say 5 girls or 6 girls or both, but there's no such thing as having both 5 girls and 6 girls in the same family. Therefore, there are no intersections to be subtracted off here. The probability of this union is just the sum of P of E5 plus P of E6. There is no minus P of E5 intersect E6. That intersection is empty. in the addition rule for probabilities, or, which corresponds to union, just turns into a plus. And that's it. That is very convenient for us. It works only because these events are all mutually exclusive of one another. To put this into practice, let's ask, what is the probability that there are at least 5 boys? The first thing I do is write down row 7 of Pascal's triangle. That is my immediate response. Now we have two choices. We can either think of these numbers as representing the number of outcomes with 0 boys, the number of outcomes with 1 boy, the number of outcomes with 2 boys, in which case 3, 4, 5, 6, 7, at least 5 boys means 5 boys or 6 boys or 7 boys. If we do it this way, we conclude that the probability equals 21 plus 7 plus 1, all divided by 128. Each of these 21 plus 7 plus 1 outcomes is contributing towards our event of finding at least 5 boys. So that equals 29 over 128. But if we wanted to, we could also think of row 7 as being in terms of girls. 0 girls, 1 girl, 2 girls, 3 girls, 4 girls, 5 girls, 6 girls, 7 girls. In which case the event, at least 5 boys, lives at the other end of row 7 of Pascal's triangle. But that's okay, because of the symmetry of these numbers, we'll add up the same 1 plus 7 plus 21. That's the same as 21 plus 7 plus 1. We're still counting the same number of outcomes in the event. Before going on to the next video, please answer the following question. We're still talking about the same experiment of randomly selecting a family with 7 children and looking at the birth order. What is the probability that the difference between the number of boys and the number of girls is at most 2?